Hey everybody! A little fun today. I should have worn my, we had the Rick and Morty intro, but today's Rick and Morty day, so it's a little, we're just here having fun today. Just got some Rick and Morty. I should have loaded up that intro. So, hey, what's up everyone? So people are asking when and where the exam is. Now the biggest thing you need to note is that your exam is for your class. Now there are classes in the same spots, but make sure to contact your instructor, and we're going to put right here. We've got exam dates and times on the Stats 1 webpage. So here, let me actually bring this down here. So let me pull this down here just so you can see where I'm at, and let's put this to the main screen. And let's make sure everyone can see. I'm going to pull the chat back up now. So we will do the chat. There you go. Let's go over here, and I'm floating away. We pulled me over there, so we're going to put me back where I belong over here. And here is where people are saying thank you for the answers in the online chat. Everyone takes the exams in person, so you want to make sure you talk to your instructor and you say, or like email your instructor or talk to them, you can do that too, and say, where are my exams? So your exams are in person, and there are the location or the times for the exams. You can see the final is 2 hours, IRL, like IRL, and the exams we're doing tonight or tomorrow. It's a long day. The exam we're doing tomorrow, not tonight, will be from 6:30 to 8, and then the exam 2 will be from 6:30 to 8 also. So important to note these times right here. You see this is all on the Stats 1 webpage. And also note that we did post an additional exam prep, which is what I'm going to be going over today. I want to make sure everyone has the answers to that. So it will be included in this video, and I'm going to be going through the examples and writing them all out. So hopefully we go here to exam prep. You can see here we have the exam prep, and I'll probably be adding this video to the list of videos to watch, but you'll see here you can click on any of these videos and go through the exam prep, which go through a lot of our review assignments. You can see here the topics on the exam, a Quizlet that I made. I really think the review videos are great though. Put a lot of time into them, making sure they show you the concepts. Has anyone watched any of these review videos that I'm hovering over right now? Has anyone seen any of the review videos? Anything? Maybe one person. So, if you watched any of them, and how are they, Griffin? So are they pretty good, Tavi? Yes. So biggest thing too is try to work out the problems, print off the test, and try writing them down. If you write down the answers and you practice them, because they're too easy, no. Okay, Gino, we'll try to do some tougher ones tonight. We've also got chapter reviews right here. What's going on with the edge of that video? We got chapter reviews, so all that good stuff. Chapter reviews, video reviews, very helpful anytime. And if you ever want a specific video on a topic, students have encouraged me to make other videos. You can always be like, hey Brian, make this video, do this thing. So always give those extra things. And yeah, so let's hop back into the main mode right here. Boop, hop back over here. And we're not really doing chapter 8 today. This was impromptu. I literally ran up here after teaching a class. So glad to know we got it all set up and running in like 12 minutes. So yeah, it's possible to hop up here and be like, let's just start teaching, as long as we're not doing so much setup. But what we have right here, I'm going to pull to the screen here, good, is I thought Terry wrote an amazing review. And so I could probably zoom in one more step. I got everything set up, and I'm going to make it all go crazy. Whoa, that's way too far zoom. Let's try to get this just right on the zoom right here. So 148 is too much. That's even better. I want this to be as big as you can see, and I also want you to kind of listen to me while we're doing this review. So whenever I encounter one of these problems, I can kind of tell where this problem is going to go. So this is a regression problem. You first want to look at what this problem is talking about right here, and we get our pen going. This problem is analyzing. We have here receivers. That is going to be the total number of receptions and total number of receiving yards. So there are receptions down at the bottom. If you see here, these are the number of receptions, which is going to be our X variable, and the total number of receiving yards is our Y variable. I suggest writing things like this on the test. We aren't even looking at the questions yet. We're focusing right in on what we can see from this, because this is going to kind of direct us when we get to later things. So we have here the X variable, which is doing the explaining, is the number of receptions. And please tell me if I make mistakes on this, because I've looked over this and I was like, oh, we can do these problems. And then the Y variable is receiving yards. And we can see this right here. This is X and this is Y. Mark up your test. Do as much as you can to make it very clear what the answers are going to be when you get to them. So now look at what we see. My class should notice there's a problem right here. What do we got going on? right here. I see a clear issue. I see a clear issue. Who can tell me what that problem is? Because we'll be getting that in a second here. What is the problem that is very, very evident? Plot thickens, Alex. There we go. No points today, but you're saying plot thickening. Thank you for all the people in the chat. That's how we do it, is give me all those answers in the chat. Pay along, follow attention. I'll kind of draw your attention to this. There doesn't really seem to be outliers here. It seems to be more an issue of the plot getting thicker. That is what I would say is the bigger issue with this data set right here. It's got a thickening of the plot. I know it kind of bends back in here, but overall this is not, this has a big plot thickening issue. Now, is the plot okay? If it were to go something like this right here, would this be okay if the plot got thinner? Would you say, oh, this is great because the plot gets thinner? Is that good if the plot gets thinner? The answer would be no. We do not want the plot to change in strength. We want even, consistent strength across, so we don't want the plot to get thinner or thicker. We want it to look consistent. So you might say, what do we want it to look like? We want it to look something like this, where the plot has equal strength. We'd like it if the plot has like equal strength. I'll move my head out of the way. So this here is the good one, and these are both bad because they both exemplify plot thickening. So we can see some examples that we need to understand that we don't want the plot to thicken. Now, we get to some good questions right here. Circle the direction of the relationship. We got this. In the chat, be telling me what the direction of that relationship is. What is the direction right there? It is definitely, if we were to indicate with a line right here, let's do a little dot right there. Where's my pens at? Did my pens go away? Where's draw it? There we go. We would get a line going up. So what I'm doing there is I'm drawing the regression line in for us to see. That is the regression line. It's definitely positive. So we're going to go here and pretend we're marking in blue on our test. And this is going to be a positive relationship in the data. So we got some points. We got 2 points on the test. What are the 3 conditions? I want my people to be saying in the chat, not my people, but my students who know. Blah, 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 ah, ah. You should know it. You're like, what the heck did he just do? Because I say this all the time. And then we ask QQ, straight enough, no outliers. And then the 4th one is plot doesn't thicken, which we kind of just talked about right there. And you'll see this later on, because I've looked through a few of these. QQ, straight enough, no outliers. Now, please, on your test, and I'd even suggest my students, to write out in full quantitative variables. And I'm going to have a fun time because I do not have the best handwriting. I know how to talk, but I don't know how to write. So we would write here quantitative variables. There's no spell check on this. We'll hope I got it right. Is this condition met? Now, by virtue of this being a scatter plot, or I would say specifically, receivers is a quantitative variable. Receiving yards is a quantitative variable, which is why I call it QQ. You ever wonder why it's called QQ? At least in my mind, it's that both variables are quantitative. I call it QQ because it's 2 quantitative variables. So the answer is most definitely yes, this is met. And the reasoning would be it is 2 quantitative variables. Now the next will be straight enough. Now be careful, I've heard people write, I don't even want to say it because they say it incorrectly. I don't want to put that out there in the ether. Don't want people to hear it. So we have straight enough, straight enough. And if you ever can't read my handwriting, be like, Brian, what'd you write? Because sometimes I can't read it either. Straight enough. And so you could say maybe it would bend up a little bit here, like someone's going to come in and be like, actually that line goes a little bit up more there if we were to put it through. But I think people are saying in the chat, yes, this is straight enough. What would be our reasoning here? Well, the line goes through the center of the data. If you look at this right here, the line, the red line I drew in, goes through the center of the data. Now you can have instances. We'll draw in an instance here of a bad example. So a bad example would be something like this. If you were to draw in a red line here to this data, that relationship over there on the right is your bad example of not straight enough. So this would be, can we say linear instead of straight enough? You should be able to. It is kind of the linearity condition, so that would, if your grader takes off points and you explain it, and you say a line well approximates the relationship between the 2 variables, and that's a good answer right there, that a line is a good way to describe this relationship, you should be good. And you can use a lot of synonymous words, but a lot of times you'll see me trying to keep everyone using the exact same wording. So that way, but please look at your tests when they're graded. I'll tell you this much, if you put linear, I would accept it. I always say QQ straight enough, no outliers, plot doesn't thicken, but linear I would accept, and I hope our graders accept also. So please look at your test. And if you put linear and you're like, the line well approximates the relationship between the two variables, that's good. This counterexample over there on the right would not be. So if we write straight enough, that would be correct. Like not too casual. Yeah, straight enough is what we call it. So we always say quantitative variables, straight enough, no outliers. And that would be good right there. Straight enough is good. That is the name of the relationship, and it also talks about the linearity. So now we have no outliers. No outliers. Oh, we're doing it in red. Sure, well, we don't want to change the color scheme going here. We're doing it in black. No outliers. And so with no outliers, what do we want? To meet this condition, we want it's going to be mind-blowing. To meet the condition of no outliers, what do we want? To meet the condition of no outliers, what do we want? Just imagine, what do we want to meet the condition of no outliers? We would like there to be, Kurt and Chris in the chat, thank you very much. We want there to be no outliers. Amazing. We got here no outliers, and we do meet this condition. Now, this is a symptom of the can't say that word. I mean, I can say it's heteroscedastic. But in 201, we're going to say this is a symptom of the plot thickening. Please note here that this gets wider and the points are more spread out. So there's really an issue of plot thickening here. So this would not be an issue of outliers. Those aren't really outliers in the data. An outlier would be something further down here maybe because it doesn't follow the trend, and that's a far outlier from the line. So this one is tricky. Oh no, I did not say heteroscedasticity. I never said that word. So with this right here, that down there, that point I put in would definitely be an outlier. And we try to make it clear at least when we draw data. We don't want to be too tricky on the test. So, you know, if we put an outlier, still got that red dot over there. That red dot over here would be an outlier to that relationship right here. And mostly that plot I just drew looks pretty good except for the outlier. So people always want, and it's good to ask for examples of, you know, this is a straight enough relationship and it's not plot thickening. It's got about the same thickness throughout. It's pretty much the same, pretty even, but then there's an outlier. So all this good stuff. This video will be available later. Thank you, Serena. You guys are amazing in the chat. I love all the answers from the students. Sometimes I always see all the questions, but then people are even quicker to respond than I am sometimes. So thank you very much. So here we are. If a player with 50 receptions and 4,000 receiving yards was added to the plot, what would happen to R? I might have done that. 50 receptions and 4,000 receiving yards. So let's erase Brian's point. Did I put them right in that spot? Oh my gosh, I almost did. So they have 50 receptions and 4,000 receiving yards. They would actually be right here. We'll go up on 50 receptions. So let's scroll up and let's go to 4,000 receiving yards. If you notice, this is where the player would be at right here. So that would be a huge outlier. That is the symptomatic. Oh, they're saying in the chat, nice answers. Because what you'll notice here, I'm going to totally destroy this nice and beautiful graphic we made here, but Randy Moss, yeah, he is, man, Patriots back in the day. You got this right here is the relationship, and then when we add in this point, it gets wider. If you see there, it's kind of bulging out more, and it looks more like a zero. So to make this very clear, let's make a cleaner drawing on this. This annotate is awesome. And so we have an original view like that. Now we add in Randy Moss over here, and he's over here, and then this would make the ellipse do like this. And it's kind of bulging it out more, and if it looks more like a 0, the correlation is closer to 0, and if it looks more like a 1, the correlation is closer to 1. So you can kind of see it visually happening there. It's making it weaker, because the tighter it is, the stronger it is, and it's bulging it out. So that would make it weaker. It would also make the slope go up. So you think about here's the original slope, and then the new slope of this, we'll draw that in on a green line because we're using green for the newness. It would make the new slope go probably up. That one's actually an iffy one. It's not going to go up that much, but that one's actually iffy and goes into a little more advanced topics than I want to get into. If you were to put over here, because this is 201 at the moment, if we put a point over here, this would definitely make it weaker, and then the slope would change and it would go up to a little bit higher, but the correlation would be weaker because it's bulging it out. The strength of the correlation is how tight it is. Do we have to write on the plots on the exam to get full credit? No, you do not have to write on the plots. Gino, thank you very much. I like to write on the plots just to make sure, and plus we might give points if you get it wrong, but you kind of write on the plot. So you do not need to write to get full credit, but never hurts to give that info. So let's continue on right here. And so just so people see the answer, the R, and please tell me if I get something wrong, because we talk about a lot of topics. Since it would bold out, the R would decrease. Using blue for right answers. We were a moment ago. So the correlation would decrease. R is correlation. Please, if you have any questions, like if you're like, what is R? Ask what R is, and we will answer it. So with that in mind, oh yes, I love these ones. These are so great. Let me zoom in a little bit on this so we can see even better, because there's blank space. So we have here the least squares regression model. Well, I need to put this little zoom out. Oh, the zoom out is so quick. Did that do all right? Yes, perfect. Oh wait, it's the same. It's just got the heading at the head again. Okay, a least squares regression line is fitted. We got the line, and here we are. As soon as I see this output right here, R is correlation. What is R squared? R squared is the coefficient. Alex, you are awesome. R squared is the coefficient of determination. Don't need to know that word. R squared is the percent of variation explained, which you see right here. So that is R squared, which is the percent of variation explained. And this other output right here would not appear on the test. Or if it does, you don't need to interpret it. And I just erased some of R squared. So R squared is what we'll focus in on for this question. And truthfully, whenever I see these things, if you came to office hours today, which a lot of people did, you'll know I like interpreting these values because it's really good practice. So even though I think I know where this is going to go, we're going to make sure we know where this output is. So if you look at this right here is y hat. Y hat is the predicted value of receiving yards. This is the equal sign, we know that. This is the value of the intercept. This is the value of the slope. And this is your x variable, which if you notice, the x variable is right there below it. You'll also notice that we have it down here that this, oops, let's put a little 0 on that. There we go. Make that look better. That is not the slope. Go away, don't. It's like, no, you cannot erase that. Wow, it wants that to be the slope. This is the slope. This is the intercept. And those are the estimates. If you notice, that says estimate of the intercept, that says estimate of the slope, which we actually have up there. So B0 is what we believe the slope might be, B0 is what we believe the intercept might be, and B1 is what we believe the slope might be. These are estimates of the coefficients you see in the model right there, which when we write the model, just to write it out nice and big, is y hat equals B0 plus B1x. I want to draw your attention to something though. When x is equal to 0, if magically x was equal to 0, then what would the value be of the equation? If we took our x and we made it 0, so if x was equal to 0, so we put in 0 for x, what does this part of the equation become then? If you solve that, what does that become? That becomes 0. So think about this. Just read off what B0 is. B0 is what we expect when x is equal to 0. Because when you have x equal to 0, well, just put here your plus. There are 2 blue pens, and I like the first one better. B0 is what we expect when x is equal to 0. So we'll talk about that in a moment. But think about what B1 means. B1 has a 1 on it, and it's connected to x. So B1 is, for each additional x, we expect y, because the whole equation here solves for y. That's what we're trying to solve for. So for each additional x, we expect y to increase by B1 for each additional. For each additional x, we expect y to increase by B1. These are important things, and they are in my other review videos, and you'll see them written out. But try to interpret this. Like, I always ask people to do this. I think we're about to see the interpretation of these coefficients on the next page. What is the fourth condition? Interpret the slope. Let's do our interpretation of the slope. The interpretation of the slope we need to do. Who can write it in the chat? And we might have, when receptions increase by 1, we expect receiving yards to increase by 13.5. Yes, For each additional reception, we expect receiving yards to increase by 13.5. Excellent interpretations, Serena and Natasha. Perfect interpretations of the slope right there. For each additional reception that a player gets, we expect their receiving yards to increase by 13.5. For each additional X, we expect, when looking at this chart, will we ever use the standard error or the t-ratio? The answer is no, Laura. Great questions, and we talk about these a lot in 320. The standard error is your uncertainty, and the t-ratio goes to the p-value to find the significance. At least in our class, we will not consider those values. You can use them for confidence intervals, and we do need to consider the significance of the model sometimes, which is the significance of the slope. Feel free to ask any question as we go through this review and look at the output. So when receptions increases by 1, we would expect receiving yards will increase by. And adding in keywords there like we would expect is good because it's not saying this will happen, it's just saying what we expect according to the model. Because if you notice, not everyone follows the trend in the model. Some people have negative residuals, some people have positive residuals, and the people on the line have a 0 for their residual. But we do have a problem that we mentioned. QQ straight enough, no outliers. Plot does not thicken. It mentioned down below what is the fourth condition. And I can't help but see these conditions when I look at the plot. So we can say here there is a problem with the fourth condition. And the fourth condition is plot should not thicken. It's all right if you say plot thickens, just understand that what we want is the plot not to get thicker or thinner. Does everyone understand that? Alex in the chat again, making sure we all know QQ straight enough, no outliers. Plot does not thicken. Now, someone asked a very important question to me. They said, what does that all mean? And what it means is, if we're doing regression appropriately, we should meet these conditions. If you are doing regression appropriately, you should meet these conditions. Can you explain plot thickening again? Yes, definitely. Here is what plot thickening is. And I'm going to add in an extra slide so I can draw around a whole bunch. Plot thickening would look like the following. So we're going to go right here and we would have a plot like this. This is a good plot right here. This is like an excellent, excellent, excellent plot. If you notice, if we put a line through this, generally speaking, the points have about the same amount of scatter from it. Now we can draw a kind of bad plot. Let's draw one that's kind of bad here. So that's a very good, does not thicken plot. If you were to talk about this one, that is 2 quantitative variables. It has to be because it's a scatter plot. So we'll put an X and a Y there. It could be like age and time or age and weight or all these quantitative variables we have, but that would meet 2 quantitative variables because you have to have 2 quantitative variables to make a scatter plot. But now we can draw in a kind of bad one, a kind of bad plot. So a plot that is kind of bad would look like the following. We put in our points and we go kind of like this a little bit and we see it right here. So if you notice, the line still goes through the center of the data. The relationship is straight enough because a line goes through the center of the data. But overall, we see that the typical miss, or the model, is making a larger error at the higher values. It's actually getting worse. The plot's getting thicker. But it's very important to note that plot thickening is not just that the plot can always get thicker. We can have issues like this. We're going to draw a horrible one here now. We're going to draw like top 10 worst plot thickening we've ever seen. So now, if you notice, at the end of this model, it's getting really, really good. It's because the model's tight around what it is. So now, this is like the worst we could see. Oops, missed the center of the data. There we go. So now, if you'll notice, this model has the worst example of plot thickening because the model actually gets way better as it progresses. The model gets a lot tighter around the line. So a lot of people will tell me the third one's good because the plot does not thicken. But wait a minute. We want it to be constant, like this one right here. This is the only one which would get the green check mark of approval that we did it correctly and we have a good plot. Now, I will say this, with real-world data, you don't always see perfect things. Your real-world data might look more like, get a little bit of thinning right there, a little bit of thickness. This would probably be a good example. This would be very good, and you don't want to overlook at it. You don't want to look too hard at your data and be like, okay, it gets thinner right there. This example right here is what would probably be a very good real-world model. These are kind of textbook perfect models, and then pretty bad, like middle one is very bad, and then one on the far side is just ridiculously bad, kind of like this model we gave you for this example. Not we. Thank you, Terry, for these examples. I thought they were excellent, and I wanted to share them and walk through these problems with everybody. So if you look, you've kind of got your real world. This is a very straight enough relationship. It has to be two quantitative variables because it's a scatter plot. And also, we have no real outliers. There's no points that really deviate far away. And also, we have plot is not thickening in any dramatic fashion. We've always done on the test that we try to make it as clear as possible. When looking at this chart, will we ever use the standard? Oh wait, that's the, I think we answered that, Serena. In this class, you will not have to look at the standard error or the t-ratios. Thank you for repeating that. And keep asking those questions in the chat. And thank you everyone for being here. I think we have like 70 or 80 people. At least when I looked, I think it was around 50, 60, and I saw it go up. The second and third wouldn't pass that condition. Correct. The second and third are both quantitative, both straight. 105, that's awesome. The second and third are straight enough. They are two quantitative variables. They don't have outliers because everything kind of follows it, but we have an issue of plot thickening. That is the plot thickening issue here. Major issues with plot thickening right there. So that would be plot thickening. That is your fourth condition for regression. There are three conditions for correlation. QQ straight enough, no outliers. There are four conditions for regression. QQ straight enough, no outliers. Plot does not thicken. And it's all right if you say plot thickens, just understand what it means. It's very important to know what it means, and then you can always be like, well, that's what I wrote. Just make sure you know plot thickening is bad. Plot thickening is bad. We do not want it to thicken. So that's why I like to say we meet the condition plot does not thicken, because we want it to not thicken. Alex, you are amazing. Keep typing those answers in the chat. Interpretation, hopefully we're not being too loud. Is that Adam? Nope. Maybe. Is that Adam?
Hello.
Adam, do you want to hand me it? We're going to have a small interlude. If you hand me it off screen here, just so we can have one more moment. Or Adam, do you want to come on camera?
You want to take my backpack off?
You can. We have, you will be live before 105 students.
Okay.
Adam, before you have to put it on before you come on if you want. Adam,
hello.
Join in the video and see. Adam is the reason we, thank you Adam very much. So everyone give a round of applause for Adam. Say thank you Adam very much. Do you want to give one last snap? Okay, you got to snap us back now. All right, we're good. So, okay, thank you. No, it's all you. Thank you very much, Adam. He's the reason we were able to borrow the Infinity Gauntlet, and that thing is actual metal. It is amazing, and we are very thankful for everything. So he came and picked it up for letting us borrow it for our photo shoots. If anyone has any ideas for our photo shoots, yeah, and Jason did all the editing. I actually did a little bit of editing on one. I'm taking 2% of the credit. Jason gets 98, maybe 99% of the credit. Do not say, Brian did a good job. Jason is the one responsible for 99.99% of the videos. Adam brought in some props, and then we all worked together. Twitch stream ready, you bet. We're trying to make this as good as possible. And you guys are the ones who are making it awesome. This review is going to last for another 45, 50 minutes. And so what do you get to watch it over there, right, Adam?
Yeah, I'm looking at the chat. Tell Maddie I said hi.
Maddie, Adam, do what? Yeah, there you go. So the man who killed Brian. I love Twitch. Yeah, we're gonna, and if people know people and if they have ideas for streaming, there's just a quick little aside, and then we'll get back to doing a review here. And we'll answer all questions. But we have a lot of really cool streaming stuff. We appreciate all of your input, and we've worked very hard. Like I did a lot of research before. Like I watch a lot of streams. I watch a lot of YouTube streams. I watch a lot of Twitch streams. And we did a lot of research on how to stream, and we tried to look at the good quality streams because education streaming is not something a lot of people do. So overall, and I'm going to go close the door. I'll be right back. I am back. So we did a lot of work to make sure we could do this in a really good fashion for everyone. We wanted this to look professional. We want it to be high quality, and we're always looking to improve it. If you notice, I now have a lot of ways where I can just click a button right here, and I can appear on a different scene. So we're using OBS, Streamlabs, and all that good stuff, and we want to make it look as good as possible. So all this good stuff right here. So I think there was a question in the chat. Let's hop back to doing our review right now. That was our little fun break. Once again, thank you, Adam. Thank you guys very much in the chat. There was a question what's the difference between correlation and regression? Great question. Correlation is kind of what we use to build off regression. Correlation is the basis of regression, so you can actually do correlation here. So correlation is just the kind of bivariate, two variables, relationship between x and y telling us the strength, direction, form, and unusual features. The four things that correlation tell you are strength, direction, form, and unusual features. Just like we got to remember that when we talk about univariate quantitative data and make a histogram, we can talk about the shape, center, and spread of it with things like unimodal, right skew. We can talk about the mean, the median, the IQR, the standard deviation, all that good stuff. I don't know if it's on here, but those are things you should review. Those are some of the earlier chapters. But then we break into two quantitative variables. And with two quantitative variables, correlation can range between values of, closed interval right here, -1 and 1. So correlation ranges between -1 and 1, but then when we square that, R squared would range between 0 and 1, because R squared is percent of variation explained. So the reason we go through correlation to get to R squared is because correlation, R, is, when you square it, R squared. So remember this though. If you wanted to, we'll do a quick question which might be on this review. What if we wanted to take and find the correlation of this data? To find the correlation of this data, which we might be answering a later question, let's go here to our handy dandy calculator. And with the calculator, we are just going to take the value of R squared and we are going to square root it. The correlation here is 96.9. Did everyone see that? All I did was take R squared and I am going to square root it. Because when you square root R squared, you get R. So the biggest thing right here that we need to know now is that this is positive. How do I know that this is positive? It's because the line goes up. You can also see the coefficient of the slope is positive or the line goes up. So the correlation of this would be 0.969. But be careful, correlation can be negative, and when you square root something, you must remember that it's going to be positive or negative. So you won't have to do things like calculating these by hand. You might have to use the regression equation in the test. So keep asking those questions. Appreciate everyone. You will not have to calculate Alexandria. Great questions on all this right here. So keep asking those questions. We will not ask you to calculate those things. I think we have an interpretation of the intercept. So now we need to interpret this value of the intercept. Who, for the people who haven't seen it, can put our blanket interpretation of the intercept in the chat? I want for somebody to put the blanket interpretation of the intercept in the chat. Remember, I'm not going to say I don't want you to be thinking about it. Thank you very much. Is there any green on it? Because Morty might be disappearing. So let's see here. When reception is equal to 0, we expect yards received to be -92. So Rena, amazing job. And everyone's doing it. It's when x is equal to 0, we estimate y to be b0. Alexandria, great job too. So what we have going on right here is we can look at the value of the intercept right here. That is b0. It is also given right here. That is b0. And remember, think of b0 when x is equal to b0. When x is equal to 0. When x is equal to 0, we expect y to be b0. And all we're doing, this is a review once again. All we are doing is taking and putting in right here 0 for receptions. And what does that do? Well, then this becomes 0. And look, the equation solves out to when receptions is equal to 0, we expect yards received to be -92. Has anyone ever heard of, we might do some of that at the end here, Laura. Has anyone ever heard of reception or yards being -92? Has anyone ever heard of getting -92 yards over a season? Is that really possible? -92 yards? Possible? Can that occur? Maybe. -92 yards? Nonsensical intercept. Nice job, Alex, right there in the chat. Nonsensical intercept. That makes no sense. -92 yards? I mean, you can get 0 receptions, but you wouldn't have -92 yards if you got 0 receptions. If we're doing receiving yards, then you'd get 0 receiving yards. Oh no, 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 no. Hopefully not. Hopefully it'll get better, I promise. I hope. I shouldn't say that. I hope it'll get better. So what do we have right here? Write out the full regression equation. I think we have that. I'm going to look in the chat because I can steal these answers. We have here that receiving yards, we'll do predicted. You don't have to do that. I mean, you could. It looks nice. That's predicted receiving yards equals, and then the value of the intercept was negative 92.03, and then we have a positive slope. And what was the value of the slope? The value of the slope is, it's going to be right there. That is the regression equation. It's given to you. Still write it out. Know that it's down here in the output also. There is the slope and intercept. Here is the slope and intercept. They are what their estimates are for right there. So 13.5, and the slope is positive, and we go back here to 13.5. So 13.5, and this would be times receptions. So that is the equation right there. What formulas will be given to you? The practice test has them. I think there's only two. You're given the regression formula and the residual formula. So we have that right there. When we interpret the intercept, do we also have to mention whether or not it's an implausible intercept? You might have to, and we'll make that clear in the question. So are we going to be given the equations like that on the test? You might be given the output. Jump output is decent to know. The test has graphics created in Jump, and the practice test has a lot of good examples of what you might see. So this review I also thought was excellent for the test, so I asked if I could cover it, and we got it, and we're covering it. Can we write y hat instead? I'd put it in context. Great question there, Nick. Put it in context with like receiving yards. You could write predicted receiving yards hat, which is the predicted value of receiving yards. Does that make sense? Put it in context. This one doesn't say do it in context of the problem, but put it in context. I like doing that right there. What does it mean for something to be statistically significant? Good question. For something to be statistically significant, it means the p-value is below 0.05. So when we look at the slope right here, the slope is statistically significant because the p-value for the slope is below 0.05. So remember, and this is good for way later in the course, if something is statistically significant, the p-value is below 0.05. Does that make sense? If something is statistically significant, the p-value is below 0.05. And most importantly, with our regression models, we care about the slope. The slope of the model being below 0.05 tells us that the slope is statistically significant, which is the relationship x and y have with each other. So that is what we have right there. The conditions for regression tell us if regression is appropriate, and then the slope being statistically significant means that there's actually a relationship between the variables, or at least one that we think is not likely by random chance. So if you had an insignificant slope, it would look flat like this, and the points would be around it like this. This would have a p-value much closer to, p-value here, we'll put about equal to like 1, because that one is not statistically significant. But remember, our line, which is the counterexample, has a p-value that is very close to 0, i.e. unlikely by random chance. Look at the difference between my example down low and our line. Do you think that those points randomly did that? Or do you think there's something really going on here that, if people get more receptions, that is probably related to how many yards they get? Like there's probably something going on there that's not by random chance. So you say, it's just by random chance. So to me, I would say it seems to me that there's actually some sort of relationship between these variables that is unlikely by random chance, i.e. this is statistically significant. The least significant model here would be the one that's completely flat, because then x and y don't really have any relationship. It's just like, well, if x changes, y, it's just the same value. So great questions, I'm hearing it. And that kind of does look like a residual plot, but it's also a model that just is not good. And the residual plot would look identical. So it looks very, very similar. Great questions. This is just a model here that just is a bad model, and it has the least significant model possible. Amazing questions in the chat and amazing knowledge. So calculate the correlation coefficient just so people can see. We went and we got the r squared, and here's r squared. To find, can I write on this still? I can write on it. To find r squared, we square root it to find r, and this will give us r, but make sure you realize it's plus or minus. It's going to be plus or minus r. I'll get out of the way of it a little bit there. It's plus or minus because we have to see if it's positive or negative. So when we square rooted r right here, so it's the square root of 0.94, and the reason we know it is positive is because the line goes up. So we had to look at the line itself, and we saw that the line went up, and that means it's a positive relationship. So if the line had gone down, the correlation would be negative. So make sure you look at it and understand if it's going to be positive or negative correlation. In addition, what is the residual for a player? Ooh, this might be a tough one. What is the residual for a player with 215 receptions and 226 yards? So this player, we know, let's mark these things here. We know that they have this many receptions. Boom. And they have this many yards. So I have X and I have Y. What could we get now? Has someone already figured it out? Oh my gosh. We know X and we know Y. What could I do with this? With X and Y, well, with X, what can I solve for with X? Remember we had an equation earlier? We had an equation. I think it was right on this page, was it not? There's their equation. Oh wait, let's go back to our equation right here, and let's take 92.03 plus 13.5, and then let's put into here the what value? Oh wait, it says receptions. That's that right there. Let's put that in here, 215. Boom. What is this going to solve for? By putting this in here, we are solving for, you can tell me in notation, because this value right here will be, and I'll erase it in a moment, that will be y hat. So the predicted y, nice answer in the chat, that is the predicted y. So do this, take this hint, take this note. If you are given numbers, mark them in notation. You notice how I put the x and the y there? And if I have x, well, I can predict from that. I can use my model to predict the receiving yards. So what is the answer to this? Oh, we can do it. You guys tell me if I get it wrong. Let's go right here. Let's show it all on the screen. And we take here 13.5 times 215. We get that. We add to it 92.03. Oh, it's negative. No. So we got to subtract from it. 202. So let's add to it 0. And then let's subtract from it 92.03. Double check, make sure you get it. Oh, Serena, nice job in the chat. And they're saying it too. Nicole, thank you very much. It's so easy to make a mistake, so easy. And so let's make it clear, because I have a mistake on here. We made an error, but we caught it. I was like, something looked interesting. That is negative. A little hard to see my negative mark there. I lost so many points on math tests because I forgot those negatives. So this is on our Stat201 site. Great stuff. So now let's take a look. The answer was, it was like 100 something. The answer is 101.36 or 110. Reading numbers is the hard part. So now we know the y hat. We'll check it out. We're almost there. Now that we know y hat, because that's what this value is, in the equation this is y hat equals b0 plus b1 x1. So that's what those are in notation right there. Now that I know y hat, I can solve for the residual, which is e. These are given to you. The residual is the actual minus the predicted. So the actual minus the predicted right here is how we get the residual. So let's just plug in our numbers. It is actually, we have here something went haywire in my thing. Someone's going to say it. I carried a number wrong. I think I typed in 21.5. So there we go. Little small error. There we go. That's looking better. So easy to make a little error. There it is. Okay. 2,810.47. Make sure to get some sleep and to eat before taking your test. There we go. Got it. Okay, nice. They're saying in the chat too. And be careful. Sorry I made an error on that. If you noticed, I think I put a decimal in the first time I multiplied that. Make sure to carry your numbers out. Something seemed weird with my numbers. Stay strong, Kevin. Like it right there. So I was wondering too. I was like, that's weird. And if something looks weird, and we'll talk about another way to check that right here. So with this right here, let's take the actual, which is 2,265, and subtract from it the predicted. There we go. That's actual minus predicted. And what will we get here with the actual minus the predicted? So let's pull up our calculator again. Actual minus predicted. Whoops. Over here on the screen. Oh. There we go. Actual minus predicted is 2265 minus 2810.47. And we get negative 0.545 and point something. Now here's what I would do. Here's another test tip. The following test tip is this. Once you get your answer of negative 545, try completing the equation solving for y hat. I think yes. I think people are giving answers here. Where did you get the 2010? That is by plugging in the value of their receptions and using the equation right there. So great questions in the chat. Keep asking those questions. How did you get this? This was plugging in their x value into the equation and then solving it. So earlier we figured out the equation, and we have here the equation, which we should have right, negative 92.03, and we'll just do a double check because that'll drastically impact the problem. So negative 92.03 plus 13.5, there's the equation right here, and it's also given to you down below. Now what I want to do is I want to see if this actually looks correct. Does everyone see that if they have 215 receptions, where would they be? So we're going to look at this graphic right here, and we're going to draw on it. Here's what I would do if I was taking the test with my knowledge of statistics. I would go and I would plot right here at 215 and trace up. Does everyone see where that line hits? Wherever that line is hitting, which I think is more about there, that is the predicted value. This value right here is y hat, very specifically the value right there. The first time I did it, I did do it incorrectly, but hopefully I would look at the model and I would say if they have 215 receptions, well then I should be predicting somewhere in the 2000s. So when my predicted value of y, which comes from this, because everything on this line is a y hat. Everything on this line is a y hat. So just understanding that that line is the prediction line, and you can kind of trace up to it. And then also I know, since they have, I think it was a higher amount than the line itself, well then, and I think we got a little bit lower than that, draw this out as perfectly as we can, because it looks like 215 is right about here-ish, and then we trace over, and we could figure out exactly what it is. But with this right here, we can figure out the actual minus the predicted, and there might be some decimals going on, but you should see about that. Perfect, yes, we did get the high 2000s. That is our predicted, and then this is our actual. So the person has a negative residual, because think about it. If we have the model, can't draw the model right there. If we have the model, let's put it right here, and then we have our line, and a person is below the line, well then the person will have a what residual? If the person is below the line, their residual must be negative. Does that make sense? So the actual minus the predicted, they are actually here and the line is higher because the line is the y hat and then the point itself is the y. So the person was over predicted. Does that make sense when we look at this visually right here? That the y hat is all the predictions the line makes, where the points themselves are the observations. So all you're seeing here is how far were you off in your actual minus predicted. I like to say residual equals actual minus predicted right here. It's a really good way to understand it, that the residual, you can just call it R, equals the actual minus predicted. And that's the same equation here, but just written in more of an easier way to understand. Did you feel like you understand regression a little bit better from hearing all this and going through these problems? Who here, and definitely big thanks to Terry, because I feel like these problems were really great and they walked through solving with the regression equation, the walking through it and doing the conditions. So remember, this will be posted live after and you will edit out my mistake. This helped a lot. How will we need to write the equation on the test? You could be given the output and writing it like this right here. That is how to write that equation. And you could be given regression output. We won't have you solve for B0 and B1 like with the equations that are on the slides with my regression solver. You won't have to solve for those. Now we need help with 2. Let's move on to that next question right here. Let's move on. Okay, let's take a look at this. We got a bunch of graphs right here, and here's what we're going to do. First thing I do when I see graphs is I write on them. So notice how this is saying that this is the 97.5th percentile. Well, I'm going to do this. I could go right here on this and use this to solve. We might need red. I'm going to do it all in red because that'll mark on black pretty well. So when will it ask for the percent of the variation y? Oh, we should do that. William, let's go back and do that because that was not a question we addressed. William asks about r squared, and let's just do the one last thing on regression right here. So if you notice, that is the r squared. The r squared is the percent of variation in y explained by the variation in x. So it would be 94% of the variation in receiving yards is explained by the variation in receptions. So listen as I say the words, and you'll hear them. Blank percent of the variation in y is explained by the variation in x. Now don't say that on the test. On the test you want to say 94% of the variation in receiving yards is explained by the variation in receptions. So you've got right there, and there's your r squared. So just making sure you understand where to put in the numbers. Blank percent of the variation in y is explained by the variation in x. Yes, great job. Answers in the chat. Are we able to write y hat instead of other words? I would try to do it in context, especially if it says in context, always give the context. This question you would not want to answer 94% of the variation in y is explained by the variation in x. You'd want to say 94% of the variation in receiving yards is explained by the variation in receptions. And we've got the answers in the chat too. Thank you for everyone writing those answers in the chat. If you're writing it, you're practicing it, and you know what's happening. And feel free, if I say something fast, or if you have an additional question, please feel free to ask. I try to repeat things a few times, and the video is recorded. So you can definitely check it out, but always ask those questions because we're all here to learn. And Terry, thank you very much. Let's take a look right here. We're going to put this right here is going to be 2.5%, and this right here is 97.5%. We could also put a mark down here and reflect this curve right here, and that is going to be where the bottom 2.5 is. So we're kind of just making some marks here that might help us out. Okay, 22% on this curve is on the outside. Does everyone see this second curve? 22% of it is on the outside. What would be on the inside of that curve? What's on the inside of that curve right now if 22% is on the outside? 22% is on the outside. Well, no, if 22% is on the outside, what is on the inside? I think, Alexandria, you're right on the 11s, so each of these would be worth 11 right here. You are correct. What's on the inside of there? 78%. So you can write this as, I guess I was using percentage before. I shouldn't use decimal and percent. We don't want to make things like that. We want to go here and write 11, 78, 11. Good stuff right there. And then you could also put a mark right here that this would be the 89th percentile. Just kind of maybe look at this for a little bit here and think about what you got, just understanding that this can be used different ways because it has a lot of information on it. Now let's go down here. Let's look at the next one a little bit. This one right here has 6% here. Sure, we'll put a percent on that one. This one is 94%. We could also use it to flip the curve, and it would be right about here to find the bottom 6%. I've done a lot of these questions in the past, and these are some of the big requests. People say, well, how do we solve all these things without the normal applet? We can give you pictures. So all of this right here, you know what I'm also going to do? I'm going to turn this z-score into a real number. Every time I see a z-score, I don't like that it's a z-score, or if I see a real number, I don't like that it's a real number. I want to see both the number and the z-score. But this one right here, we're going to take. Now, if you notice, this problem deals with a normal curve with the following. Does everyone see that this normal curve is 14 and 3, which means the center of it is at 14, and each standard deviation goes up by 3. So each of these standard deviations are 3 right there. So if I want to turn 1.55 back into a number, I want someone to take a guess what this would be close to. And look at this right here. If you were to trace and look, give me a guess of what the number might be. Look at where it would hit on the curve, on a real number. Just take a guess of what it might be. And by taking a guess, you might, and you're just looking at, wait, that's at that spot on the number curve. Sorry, and Red, we will answer that in 2 seconds. So good answers. 18.5, excellent answer, good guess. A z-score is found by the formula. It's going to be observation minus the mean over the standard deviation. So this is what these are right here. These are observation minus mean over standard deviation, and that solves for a z-score. And z-scores always have a mean of 0, and that's where the mean is at, and a standard deviation of 1. Because think, if you did mean minus mean, what would be the difference of the mean from the mean? That would be 0, and so you'd get 0 over standard deviation. So this right here turns things into z-scores, and z-scores are standardized units of measurement. So that way you can tell how far something is away. Something that is 3 z-scores would be an outlier and unusual. Red, thank you for asking those questions. Keep asking them, and I'll answer every question in the chat. So will we be given that equation? I'm trying to think. Check the practice test. I'm thinking, I don't remember. I'm trying to remember what equations. I hate to say yes or no when I'm not confident. What is on the practice test is what you will be given. So this is just observation minus mean over standard deviation. And so now let's turn this back into this. I want everyone to think for a moment what the z-score means. Since this is a z-score, all we're saying is that the observation right here, well, let's go back to it. Well, sure, let's do this one. Think about that. A z-score of 1 is how many, it isn't. I think he's right. I think he's right. Arthur, that sounds correct. A z-score of 1 is how many standard deviations above the mean. A z-score of 1 is how many standard deviations above the mean. Anyone got? Just think about it. A z-score of 1 is how many standard deviations above the mean. Who's got it in the chat? 1. You're right. So wait, the mean is 14, and the standard deviation is 3. So with that in mind, we just go up 1 standard deviation. So if you go from 14 and up 1, you'd get to 17. So that explains that up here on this graphic up top, 17 is there. So, well, what would we do? We would need to take the mean, and we would need to add to the mean the z-score times the standard deviation. So this is just a reworking of the formula to solve for y. So all we're doing is we're taking the mean and we're adding to it the z-score times the standard deviation. We're taking the mean and we're adding to it the z-score times the standard deviation. So this right here would be, we'd take the mean, well, let's first do the z-score, times the standard deviation of 3, and then we add to that the mean. So all I did was plug in the mean plus the z-score times the standard deviation, and people were guessing 18.5. You were very close, because that value right there is at 18.65, I think it was, 18.65. I think that might be a value we might need later. The reason I'm doing this is there's a lot of good problems to come on this. But there's so much to understand, so many questions we could ask. I could make up 10 more questions from this, Missy could make up 10 more questions from this, Dr. Panel could make up 10 more questions from this, and the questions could just go on and on and on. But just understanding what is here and how to use the information is important. And so we'll look at the questions in a moment, but I want you to know what to do with this and maybe how, especially, to turn a z-score back into an observation. So does that look like it's about at 18.665? Yes. All I did was add back on the z-score by timesing it by the standard deviation and adding it to the mean. So very, very good stuff right there. So that one, I think, is one of the questions below. We'll skip the rest of the graphics now, but go to the questions. What % of Arctic foxes have a weight less than 10.32? Are they all different tests? There's different versions, but if you're in it, you'll have the same probability of having it if you're in panels, Higgins, Missy, or my class. So everyone will have different versions, but different versions, but like A and B, but you will not be getting different tests in panels class than you are getting in my class. So with this, oh, they already have the answer? You guys are amazing. I think we already did that because this answer was the 17.68. So remember how it said 17.68? Well, we already answered it by doing this, because this spot right here is where this is 10.32. 10.32 is here, and we did it. We solved it. We already solved that one because 11% is below there, and we used this graphic right here to figure out the percent that are expected to be below, and that is specifically this portion of the curve. A little hard to see the highlighter right there, but that was the answer to A, and we actually already figured it out by marking this curve. I've done a little bit of this, did a little practice on it to see what the questions were, but the answer is 11%. Now here's the thing, we're not using yet the 68, 95, 99.7. We are using these curves, and I want to say something very specific. If you are given these curves and you have the opportunity to use them, use these curves. So you see the answer is 11%, because we can tell the area below 10.32. That's where that spot is on the curve, and we can see it right there. Good stuff. Let's take a look at the next question right here. What percent of Arctic foxes are expected to have a weight higher than a z-score of 1.96? So with this right here, where do we have a curve that looks like 1.96 is there? And the answer is the top one. So if you notice, a z-score of 1.96, how did I see this? Because this is a z-score of 0, this is a z-score of 1, and this is a z-score of 2. Does everyone see that I'm taking a guess that this is about 1.96? Now I know I'm saying I'm guessing that, but let's take this observation and turn it into a z-score. To turn that observation into a z-score and confirm that this is the z-score, we're going to take the observation minus the what, be saying in the chat, over the what. Observation minus the, I should be saying it, I should be saying in the chat. Observation minus the, observation minus, I'm stuck, oh no. The close, it's not really the predicted, it's the mean, and Anita, nice job there. Observation minus mean over the standard deviation. This is the formula we put below, and if you'll notice here, I'm going to mark this in a different color. This is the mean of the distribution. Ooh, it's hard to write very small. That is the mean of the distribution, and that is the standard deviation. The 14 and the 3 are the mean and the standard deviation. I put them in the population format, but still they could be y bar if we're doing an estimate and s if we're doing it. But those are the values that are being put in there. If you see the 14 and the 3, those are the values I'm putting up right there. So let's check to see if this is a z-score of 1.96, and it should be. So let's do here observation minus mean, divided, oops, didn't hit the minus, minus the mean, divided by the standard deviation, and 1.96. Visually, we could kind of tell it was the answer. Now don't just go off the visual. Don't be like, visually that looks correct, so I'm picking it. But remember, what I did is I looked and I saw that this is a z-score right here of about 1.96. Just, it's a little bit below 2. If you notice, when I put in my z-score marks, which I'll highlight where they're at, there's my z-score marks right there. You can barely see them. But my z-score markings told me that that is a little bit below 2, so maybe that's a z-score of 1.96. And then I calculated it to confirm it, but if I was short on time, I would just be like, I think that might be the weight of Arctic foxes right there. That is the 97.5th percentile or the top 2.5%, which I believe this was asking for the top right here. And let's put in the answers. This was 11%. And what percent are expected to have this? This would be 2.5%. What percent of Arctic foxes are expected to have a weight between 14 and 17.68? 14 and 17, wait a minute. Let's clear this graphic off, because you know what I see? Let's make this nice and neat again. Got to do all massive erasing on your test. I see 17.68 right here. So with this, let's draw this in right here. The area is as follows. The area is this box I'm drawing. How much area is in that box? How much area is in that box? An exact answer, and we might have, I think, close. People have a close answer in the chat. The whole box has 78, with the white included. They are saying it in the chat, 39, unless I've made a mistake, which I think we have not. Because now this is 39, and this is 39. Because it's half of that box. Sorry, it's a little hard with the red and the blue there. But that whole thing is 78, and then half of it is 39. So we're using this graphic again. There can be some graphics you don't use. You won't need to use all the graphics if we give you them. Just different graphics can lead to different answers. But it's clear to see here that it is 39%, and we did a container right here to see it's 39. Tricky question. Good job for those of you who figured this out. That's a really good question. I like that one a lot. Not that I don't like any of these, but that was great. Now we need to figure out and tell me if I make an error, please. We already made one today, just one. What percent of weights of Arctic foxes represent the 20th percentile? So the 20th percentile, let's think about it. Where would that be on the curve? Now, I'm just going to do my own kind of drawing here. Let's add in a new slide. Here's what I know. I know when we talk about percentiles on the curve, the 20th percentile needs to be in a certain spot. Let's use our 68, 95, 99.7 rule to think about this. Because if 68% is between -1 and +1, that would make 1 the what? Let's do this. This is the practice right here. 68% inside, what percent would be outside? 68% inside, total outside. 68% inside, total outside is what? 68 inside, total outside is what? Total. Everyone else goes right to the big numbers. If 68 is inside, total outside is 32, and then half of 32 is what? Because we're saying right here that all of this is 32, so then half of 32 is 16%, which means the portion of the curve from here below, I didn't draw it perfectly today, should be 16%. And what is at the middle of the curve? So if this is the 16th percentile, the middle of the curve is the 50th percentile. So that means the 20th percentile should be somewhere inside of here. And hopefully my brain, I'm like double checking with my knowledge of statistics. The 20th percentile is somewhere inside of there. That's where the 20th percentile is. I'm also going to mark here, because I know people can be tricky, this is where the 80th percentile is. The 80th percentile would be somewhere around here, and the 20th percentile is here. So this is kind of my helper graphic that I'm drawing to get this right. How did you get 78 in graphic 2? I'm a little bit behind. Great question. 78%, because we know that this total is 22%. These black areas total are 22, so that makes that 11. That makes that 11. Thank you, Serena. Great question, because 11 on the outside, 78 on the inside. Cut that in half. Pretty tough question because it requires a few calculations right there. But always try to draw on these and do everything you can to be like, well, what numbers, what curves are helping me out? These are some of the tougher questions on the test. And there's a good bit of regression and there's a good bit of normal curve, hence why I'm here today. So yeah, Megan, feel free to ask those questions. I'll answer all the questions. You are free to ask them. If you look at this graphic right here, I'm a little bit before -1 and +1. And I saw a graphic just briefly. Look at that right there. Look at that graphic. Wait a minute, you know what I could have done? I could have done it. We go right here and we put 20% right here, 20% here, and then we put 60% right here. How did I know that each of those white areas there are 20%? How did I know that? How in the world would I know that? Any ideas? If there's 60% on the inside, there's 20% on the outside. And just so you can see, does that look like the graphic I drew over here somewhat? If I did a little shading on this and we shaded this in, does my graphic that I drew look kind of like the graphic down here? I kind of got lucky that the graphic kind of looked like mine. If the middle is 60%, then the outside's total 40, and right here is going to be it. But we got a problem. The problem is I think it wants the weight. We right now have a what? Say, Brian, that is a, and that's the wrong one, we want the -1. Brian, what you are circling here is specifically a what? Brian, that is a, who knows what that is? That's not the weight of a fox. A fox can't be -0.842 pounds. That is the something of a fox. The z-score, that's the z-score. Foxes can't weigh negative weights. That's preposterous. So we would go here and we'd take this. And we need to take this z-score and turn it back into an observation. Write down this formula if you want, but remember we're just going to take the mean and we're going to add to it the z-score times the standard deviation. So that's z-score times standard deviation. You're just adding it to the mean. And if you had to take a guess, let's do this. Remember, it was right before there. If I'm guessing, I'm going to get a little more than 11. Does everyone see where I'm marking that graphic right there? Because this graphic has the numbers on it, so I can use it to make an educated guess. Don't give this as an answer, but it looks like it's like 11.3. So my guess is 11.3 because of that graphic. Because that red line I just drew is in the same spot here, so that looked to be up there at the top, which you can barely see. 11.3? Let's see how close I am. I hope I'm one decimal place accurate. Fingers crossed. So now we're going to take the mean and subtract from it that many standard deviations. So we're going to go standard deviation of 3 times 0.842. Oh no, I'm more than one decimal place off. I'm very close. It's 11.47. And that was pretty close right here. So remember, we have here that we're taking, I'm going to write the formula I just did. I did 14, which is the mean, and then we do plus, and the z-score is negative 0.842 times 3, because that's the standard deviation. So that was the mean plus the z-score, which was negative. You could subtract it, but just remember it's negative. And so y bar is the mean and y hat is predicted, and that is for regression. Great questions. What's the difference between y bar and y hat? Excellent answers, everyone in the chat. Y bar is the mean of y hat is the predicted, y is the actual. Remember, in my class I said, everyone, put in the back of your notebook all the notation. And so that's my suggestion to everyone in every class. Flip to the back of your notebook now and just write down y is the actual value. Y hat is the predicted value. The question, I was reading the question too at the same time. Isn't 0 the mean? Yes. On the standard normal curve, Windows summary, random thing right there. Go away, Windows summary. On this curve, the z-score curve, it is 0 and 1. But that is a z-score curve. So the mean is 0 when we standardize it to z-scores. So 0 is the mean on the z-score curve and 1 is the standard deviation, but then we would use it in context of the problem, which has a different mean and a different standard deviation. So I kind of went right into the graphics. We should edit the video and put at the start. We want to understand the weight of Arctic foxes, and the weight of Arctic foxes are normally distributed with a mean of 14 and a standard deviation of 3. I love solving these problems so much that I jumped right into it, that we have here that the Arctic foxes have a mean weight of 14 and a standard deviation of 3. How do you draw the deviations for the curve? Yeah, let's talk about this right here. I do understand how you draw the deviations for the curve. Okay, hopefully, let me see if I can answer that. And please tell me if I'm not answering it well enough. Okay. So what we need to do is we need to go here and we need to draw the curve itself. So you just get some practice drawing the curve. And if I'm drawing this out for myself on the test, I'm going to put here 0 at the center. I'm going to put 1, 2, and 3. Then I'm going to go -1, -2, -3. Those are the z-scores, which will always be the same. So what you could do, miss the mark right there, and then you would go normally distributed with a mean of 0 and a standard deviation of 1. And then when I see a question that comes up that talks about the Arctic foxes, and it says that the Arctic foxes are normally distributed with a mean of 14 and a standard deviation of 3, I can draw below this 14, and then you just go up by 1 standard deviation each time. 14 plus 3 is 17, plus 3 is 20, plus 3 is 23. Minus 3 from 14, 11, minus 3 from 11, 8, minus 3 from 8, 5. And so there we go, we draw it in right there. That gives us our curve. We've got the z-scores in black, and we've got the context, the Arctic fox context, right there. So that way, if you look at your curve and you saw a mark right here, you could kind of guesstimate where it's at like we were doing. That has to be a little more than 11, and also the z-score was like negative 0.84. So this right here, thank you for, oh, we got a, wow, the subscriber thing. Thank you for subscribing. Man, I love we got Streamlabs on in here. I think, oh, when it's public, Streamlabs works. That's why Streamlabs is working. It doesn't work on my unlisted streams. Oh, just noticed Rick Morty. Thank you very much. So you make the units in proportion of the equation. Yes, so you take right here, you've got your z-scores, which I'm pointing at now, and then you've got your context. So this is the way I like to solve all my problems, is you always put the z-scores up at the top, because z-scores are always the same. It's just 0 is the mean, and then you see the mean over there at 14. That is the mean of the distribution. And then we also do the in context below. The video from yesterday should be public on the YouTube. Is it public? I can't confirm that right now, but it should be one of our latest videos. The Kahoot should be on there. If it's not, I hope it's there. So fingers crossed that the Kahoot from yesterday is still on YouTube. It should be. Does anyone see it? Yeah, and the video should be posted. It should still be a public link. So great stuff. Thank you, everybody, for making these reviews great. Alex, how many people do we have watching? So we have the 20th percentile right here. What weight of Arctic foxes represent that? We solved it. We did solve it, right? It's 11.47. So 11.474. Hopefully I don't make an error in here. 87, still amazing. Arctic fox that, an Arctic fox with a weight of 9.335 would fall in what percentile? 9.335. You know what I'm going to do? We're going to go crazy on these graphics right here. 9.335. So does everyone see? This, I think, is the big, tough question. If you look, 9.335 would be, we'll clear off this graphic. This tablet is amazing. So 9.335, it came back. There we go. 9.335 would be right. That's way too high. It needs to be a little bit lower than this. It's going to be about right here. That's where about 9.335 is, which means it's here. Ooh, wait a minute. It looks like it's also this. This is a tricky one. This is some of our hardest. And great job, Alexandria. You got it right. Amazing job. Because I want you to imagine this. I wish I could do this in real time right now. Take that graphic right there and flip it. If you took that graphic and flipped it, so literally you just flip this area, so now the area over here would be the white area. So we'll redraw it right here with that as the white area. Do you see it? That's the spot I want. But how about this? Let's confirm that because the negative z-score would be 1.555. Does everyone see that right there? Negative 1.555 is where this mark I put right there. This spot is a z-score of negative 1.555. And what would the observation be? So remember how we turn observations back? We take and times that by the standard deviation. Oops, too few fives. No. So 1.555 times 3, and then we're going to subtract that from the value there. So that equation I just did was 14 plus negative 1.555 times 3. 14 plus negative 1.555 times 3, and then I found that that spot is at 9.33. That spot is at 9.335, which I think is where it wanted us to do. And since this area here is 6%, that area there is 6%. That is a tough one. That is probably one of those level 8 or 9 questions. It's one of those ones even great students might miss. But just think about what you can do and look at the graphics. As I said, I could write 10 more questions with these right now, and understanding what the graphics are showing you and knowing how to kind of take in this information. These are tough questions. Do you know if it's Monday's lecture at all? I think they're asking questions in the chat. So that should be the answer. It should be 6%. Amazing. And people are helping on the chat. And is there one more here? There might be a few more. 6%. We'll go for another 30 minutes or so. Thank you for everyone watching. So, this is a good one. Another great one. The speed limit is 25 miles per hour on Cumberland. During the construction along Cumberland Avenue, assume that the speed of cars follows the normal distribution. So it's telling us it's normal, with a mean, so there's the mean variable, and a standard deviation of this right here. We're slowing down a little bit on this one. Find the z-score for the speed limit. So that's saying, how unusual is the speed limit? So the speed limit was 25 miles per hour. And think about this, the speed limit, it'd be unusual to go the speed limit. So it'd be unusual to go the speed limits. So let's take a look right here, and we're going to z-score it by doing the observation minus, and we'll write this right here, y minus y bar over s equals z. So the speed limit is what we might observe someone going. And I think about this because I know what Terry's pointing out. He's saying the speed limit is above the average. The speed limit would be a little bit high to go, because if you remember construction of this, the speed limit would be a little bit faster than you would expect to go. So we're just going to take right here, and we're going to subtract observation minus mean over standard deviation. And it's 1. It's perfect. It's exactly 1 above. Nice and neat answers right there. Please tell me if I get something wrong. Everyone in the chat saying it. Thank you, Chris and Megan. So, and we got another subscriber. Awesome. Thank you guys for subscribing. So thank you very much, Ford. This is how streamers. Do you guys see Streamlabs in the chat where it says? I think you guys see that. So I didn't know the public streams do that. So what % of cars would you expect to be going? Oh, nice. Perfect. Let's just put right here the z-score of it. What % of cars would we expect to go over the speed limit? This is an amazing question. I get excited when we get to use the 68, 95, 99.7 rule. Because in between -1 and +1 is 68% of the data. Nice job, Adriana, already getting it right here because we're doing the outside trick again. The inside-outside trick with right here, if 68% is inside, then we would expect, and it says over the speed limit, so great job. I'm going to point out that Lila, sorry if I'm mispronouncing right there, pointed out that we would have 84% under the speed limit. So if you were to ask this question differently, there's 16% above, which means we would expect 84% of people to be going below the speed limit. Does that make sense right there? Because look at the numbers I have and how they add up, that if we have 16% above, we'd expect 84% below. So you can kind of see it visually right there, and this is what we'd want to do. The reason that you got an exact z-score right there in this question, just the way we formulated the question, not we, Terry. Thank you so much, Terry. The reason this question was formulated on the top one this way is because it gives a z-score of 1, which is on the empirical rule numbers, which you can then solve and say, well then I would expect 16% because 68% between, 32% outside, and 16. Now I will say this, on the test we do make it very clear when to use the empirical rule numbers. This is a huge thing. If you're taking the test, when you're taking the test, which you should use the empirical rule numbers when it says use the empirical rule numbers. If it says use 68, 95, 99.7, use those numbers. So if it doesn't say use the graphics like we were doing earlier. So these questions leaned on the graphics, where the question now is having us use empirical rule numbers. So the only thing I would change if we were doing this on a test is I would say use the 68, 95, 99.7 rule. If a car is captured on the radar at 28 miles per hour, would you consider this speed unusual? Justify your answer. Well, to figure out if it is unusual, we must turn it into a what? To figure out if it is unusual, we must turn it into a what? How would we know if that's unusual? What would we do with that number to see if it's unusual? Like, is it unusual for someone to be, they're already figuring it out. Is it unusual for someone to run a mile in 7 minutes, 6 minutes, 5 minutes? Well, how far is that from the average? Turn it into a z-score. So observation, let's go blue again. Observation minus the mean. So observation minus mean, we've kind of got it written up here. You see the mean is still the same. It's still the same mean, but it's a different standard deviation. And I have preferences. I'm going to tell you some of my preferences right here. So when we talk about if a z-score is unusual, usually, and this one is going to be over 2. So this one is going to be a little interesting, and we'll talk about it for a moment here. This one's going to be like 2.3, I think, as long as I do the math correctly. It's 2.21. So this z-score is 2.21. On our curve up here, it would be somewhere over about, let's go to green, let's go to black, better. It's going to be about there. So that's where it would be. It's kind of unusual. Now, if I were to turn this into a test question, I like to make things very unusual or very not unusual. The speed limit up here with a z-score of 1 is pretty not unusual. Z-scores of 2 are kind of outliers. Z-scores of 3 are definitely outliers. Think about this. If you were to say that the test has an average, let's go here with normally distributed of 70 and a standard deviation of 10, then an 80 would be a z-score of 1, a 90 would be a z-score of 2, and 100 would be a z-score of 3. So scoring a 100 would be very high. Just think of here, 100 is 3 standard deviations above 70. 100 would be more unusual than 90. So I would classify this as kind of unusual. And if I were to give my answer, I'd say z-scores of 2 are kind of unusual. So it's pretty unusual to get someone going 28 miles per hour. Now, what I would do if I was writing this, just we all have different preferences, is I would go here, sounds so bad. What I would do, I would put this like 31 miles per hour, and now we're going to see here that if this question had 31, this is going to be even more unusual. No one ever taught me how to write till I was 30 years old, and then they said, we're going to teach you how to write. It shows. So my handwriting is horrible. Sorry, everyone. So with this right here, we have that 31, and now let's z-score this. We just kind of altered the question. 31 minus 22.53 divided by 2.47. The z-score is now 3.42 or 3.43 rounded. My answer to this question would be, this is a very unusual speed. It is more than 3 standard deviations above the mean. And we just did a small change to the problem right here to turn this into a more unusual z-score because we just made them go faster. That's all we did right here, was make this problem a little different. So that's not the problem that was there originally, but it's just more unusual. So would it be unusual for somebody to go the average speed? What would be the z-score now? Just quick review, because I haven't heard from the chat in a little bit here. What would be the z-score if somebody went the mean? If the question was talking about the mean, what would be the z-score of driving the average speed? 0. Serena, nice answer in the chat. And that would not be unusual at all because it's what you expect. It's at the center of the curve. So all you're doing there is seeing how far is the mean from the mean. And the mean is 0 standard deviations away from the mean. So that would not be unusual. Ooh, we get to a tough one. What percent of cars would be driving with 28 miles per hour slower? Now remember, we just z-scored this, and I think it was 2.2-ish. 2.2-ish, which is good enough. Here's what we're going to do. We're going to draw our normal curve, and once we get the normal curve, we're going to put 0 on here, 1, and we're going to put 2 and 3. We'll put the other numbers just for fun, but those are the ones we really need. And now what we're going to do with our curve is we're going to draw our line. We're going to draw the line, and I'm going to do one more thing on the curve too. We're going to draw our line right where the z-score we found was, right here. Now I'm going to do this because this is how I would do it on the test. On the test, I would take the number 2.47 and I'd put this below it too. Remember how I was drawing earlier with the context? So it's 25, or nope, 22 point something. Why do these have to be decimals? This is 25. And the mean is, the mean of the curve is 2253. So 2253. And then that is 25, gotta love decimals. And 25 plus 2.47. And I think we're getting some good answers right here. I'll double check, 27.47. So a lot of decimals. You might annotate some decimals, but does it make sense that I would label these numbers? And you can see here, does it look like to you that this is where 28 miles per hour is? Does that make sense right there? Because the standard deviation of 2 is 27.47. Does that look like where 28 miles per hour would be if right here, this is where a standard deviation of 2 is at 27.47, and we are a little above that. If that visually looks correct, you're doing it correct. Now we want to figure out the percent of cars that are going slower, and great job in the chat. Adriana, you got it. And also everyone else, Megan and Alex, and thank you everyone for answering all these questions. Griffin too. Keep up the answers because we're going to take an arrow here and we're going to draw an arrow that is, let's do a different color. We're going to draw an arrow that is too small and we're going to draw an arrow that is too big. This is a tougher one, but let's add in some helper arrows. We're going to draw this and we're going to draw this. So I want now, the inside green arrow has how much area in it? The inside green arrow has how much area in it? Why are those specific numbers? So the inside arrow, slightly unusual. I would, Alex, and I always want to make them very unusual. So Alex asked, would I say slightly unusual? I would, but I like large z-scores if we're going to test you guys on it to see if it's very unusual, and it makes it a little bit easier to that's very unusual. That's not unusual. So usually we go for the more extremes or the less extremes on the test. So what is the inner green arrow, the kind of this one, how much area is that covering right there? So that'll help explain to people how we got these answers. The inner green arrow is covering how much area? How much area is that inner green arrow covering? Any ideas? Any guesses? It's between -2 and +2. 95%, nice job, Serena, thank you so much. 95%, which if 95% is on the inside, what's on the outside? 95 on the inside, 95 inside, boom. 95 inside, what outside? 95 inside, 5 outside, and then we divide that in half right here, 2.5. You know what we can do now? We can just add up from here over, which means this arrow right here is 97.5. Now we're going to have to do some erasing because I'm going to have to draw on it again, but that's how those numbers were taken. That's how we got it. Now we need to go and do the same thing with some green arrows, which are going to help us out. Try to make the green go away, but it's going to erase everything if I do that. So let's go here and go from here to here. How much area is there now? How much area have I graphed between -3 and +3? 99.7. What is outside of -3, +3? 99.7 inside. Total outside would be what? Oh no, don't worry. Total outside is 0.3. So now we'd get 0.15, and over here is 0.15. If you draw numbers, make sure they add up to 100%. So 0.3 total divided in half for 0.15, which means if we add across this way, going from here over, this would be 99.85%, which means it has to be less than 99.85, but more than 97.5. And that is how those answers are obtained. That is a pretty tough question, probably a level 7 or 8 question. So we won't have all the questions on the exam be like this one. A little bit tough, a little bit tricky. Try drawing it out. Try to reason through it. There's a lot of partial credit on the exam. So if you're taking notes right now, be like, try to solve the problems. Try to draw what you can. A lot of teachers, a lot of graders, we make sure they know, give partial credit. Because if you leave it blank, you get no points. If you show you know something and you're doing pretty like, you get kind of close, you give some answers that are close, maybe you write instead of 97.5, you write 2.5 and 0.15, then you've just reversed the way you're doing your arrows. You did the upper arrows like the area above it. So we would just maybe take off a point or two, kind of tops, because you knew how to do it, you just made a mistake. Good questions here, and thank you everyone in the chat. I think we got one more page right here. We got 2 more pages. Let's do it. Okay, looks like we're going to about 5:30. So we have here box plots. Which country has the greatest range right here? This one's an easier one because it has the outlier. If we have it right but we don't show our work because we know it, you will still get the points. You will still get the points. If you get it right, you get it right. That's the way I grade my exams, and I tell my graders to grade it. If it's right, it's right. But show work just to make sure if you get it wrong, you get points, because if you put the answers. But we also kind of know where the answers come from, so we can kind of look at it and be like, okay, they did this or this. So yes, great job. Which country has the highest median? Let's put some arrows where the medians are at. Let's draw this. You ready? Q1. Oh my gosh. Bright lights. I've been under some bright lights. Q1. That was to test you guys. Median. This is the min. And let's go here to Q3. And let's go here to the max. There we go. Make sure you know those spots in the box plot. This line right here, if you're wondering, is the grand mean of the data. You won't need to know that. Which country has the highest median? You guys have already done it. You've answered because that is the median. And that is the highest. The line in the box plot is the median, the line in the box. The box represents the what? I think it's Q1 to Q3. The box represents the what? The IQR. That is the range of the middle 50%. That is how far the middle 50% spans. So you can kind of see questions we could make up. Which box plot has the greatest range of the middle 50%? Greatest IQR, smallest IQR, highest Q3, lowest Q3, greatest Q1, lowest Q1, greatest min, greatest max, greatest median. All these questions can be written. So we have the country with the highest median is Italy. I want to go to Italy. Be nice. Italy. So go there on honeymoon. That'd be great. So which one describes the shape of the distribution methane emissions in Romania? This one is a little tricky. I don't know. I say I don't know. Box plots are not the best. And I do agree, Adriana, I think we're going to go with your answer. Skewed to the right, right to the high, left to the low, whatever way the tail goes. If you notice, this is pulled out a little bit in this direction and it has an outlier. Box plots are not the best for looking at it. And how do I know that's to the right? Because this is the high side right here. So this is the high side of the data, so it's pulled to the high side. It's slightly symmetric. I would actually probably ask about Turkey. Turkey is even more right skew. If you look at this, here's your marks, and look at how they start to pull in the right direction. Does everyone see those marks I'm putting in? I'm going to put them in a little more in blue. But if you look at those marks on the data at where, let's make it even clearer. So if you look at these marks in the data going from the min to the maximum in Turkey, it pulls out more towards the high side. There's the Q1, the median, the Q3, and the max, and it pulls in that right direction. So Turkey is definitely more right skewed. It's probably the most right skewed distribution. This one right here pulls a little bit more in the left way because if you look, it's more spread out on the left side. If you look at how just it kind of spreads out along that way, to figure it out, I would just turn the box plot to the right. You take those box plots, just drop them like that, and you can see it. Because then the number line goes in the right direction. You'd want to drop it this way. Make sure to turn it that way. Actually, let me do it the opposite because I'm mirror image. You want to turn it this way. Does everyone see we're turning it this way? And then your number line will go in the right direction. So that is a great answer, Serena. Great advice. And right to the high, left to low, whatever way the skew goes. Just going to do that all day. And which of the following statements is false? Oh my gosh, these are the toughest ones. Italy's emissions is more than Italy's minimum. So Italy's minimum, Turkey's minimum. Italy's minimum is this. Is it higher than Turkey's minimum? Is Italy's minimum higher than Turkey's minimum? The answer is true. That is true. So that value I pointed to is higher. Japan's median is less than Turkey's median emission. Ooh, oh, that's also true. There's Turkey's median. There's Japan's median. So Turkey's median is higher than Japan's median. That is true. Romania had the year with the highest emission. Ooh, if someone misses that outlier, that's one of those ones outliers tricking you. That is true. So unless we've made a mistake, the next statement's going to be false right here. So unless we've made a mistake, the next statement's going to be false. New Zealand was the least consistent. And I would say had the least variation. New Zealand is the most consistent. I'd probably say has the least amount of variation. New Zealand has the least amount of variation is a true statement. Was it said is the least consistent, did it say? Let me double check the wording. It's the most consistent. So their emissions are very consistent. So the statement of least consistent is false. The least consistent country was where? What is the least consistent country in their emission levels? The least consistent country would be which country? Hint, it'd be the country with the greatest range. Romania, great answer. Romania is the least consistent. New Zealand is the most consistent. And feel free, if you're wondering what consistent means, on the test I could tell you that means it kind of has like less variation. So least consistent would be more variation, and more consistent would be less variation. More consistent. Like if your test scores are consistent, you get the same grade. If your test scores are not consistent, then you get a wide variation in grades. Tricky question right here. That was a tough one, especially with the wording, but it was a good one. That was a very good review of those box plots. Well, let's do a small circle. Approximately, what value is the 75th percentile of Japan's emissions? So we need to know, did we mark Japan's emissions? We did not yet. 75th percentile, ooh, this is going to be a tougher one to draw. It's going right about here. That is the 75th percentile is marked by Q3, maybe 44,000 or so. Decent guess, just right there. So decent guess, that is the 75th percentile because that's the box. The box contains the 25th to the 75th. So that is the 75th percentile of Japan's emissions. That is a 44. My 4s look like 9s. So 44,000 about. Let's do an about equals. About equals. Approximately what value is Q1 for emissions for Romania? Q1, just doing our tests of these spots. So now we need to trace a line over here. And let's go to Q1. Oh, wow. That's halfway right there. So we can go 32. Oh, let's redraw that. So that's 32,500. Awesome. That one I like. That one's excellent. That would be great. So if you notice, all I'm doing is knowing where my spots are on the box plot. I need to know all of these. Do not forget that Romania has that outlier, which is the max. Do not forget those things. Those can trick you on exams. So this one right here is 32,500. I think we've answered all those. Great stuff. We have 2 more pages. We got this. Okay. Considering the following jump output on whether students from the Stats 2 exam did better on exam 1 or exam 2. So we have section A, and if they did better. So they did better on exam 2 than on exam 1. So these are the students right here, and I see a question. Box plots are always skewed right in order for them to have medians. Serena, so if a box plot is skewed to the right, when a data set is skewed, we'll use the median as the center, and we'll use the IQR as the spread. So box plots are really good to display skewed data to see those median and IQR values. So if a box plot is skewed to the right, or if data is skewed to the right, you'll use median for the center and IQR for the standard for the spread. Median and IQR go for skewed data, and mean and standard deviation are for normal data. So I didn't mean skewed to the right, I meant skewed. Yeah, if a data set is skewed, you will use the median and IQR. If a data set is normal, you will use the mean and standard deviation. Great question in the chat. So here we are. Let's make sense we know what this is. These are students who are in what section? These are students in section A who did better on exam 2. So 66 students in section A did better on exam 2. 21 did not. Ooh, this looks good for us then. What percent of students in section B did better on exam 2? Now wait a minute, this sounds like a conditional distribution to me, because we'd have to say given someone is in section B. So they might be saying in the chat, normal data can have medians too. It doesn't have to be right. So we can get the medians, but we would not use them as the center. So normal data, we can find the median, but we won't use that as the center. If it's normal, we'll use the mean as the center, and we'll describe it that way, so we'll have a normal distribution. Great answers. And so what percent of section B students? So given someone is in section B, they did better on exam 2. And that is about 60% right there. Keep those questions and answers coming in the chat. The best way to watch this is to be partaking in this right here. Is normal data symmetric? That is correct. Normal data is unimodal and symmetric. Normal data is unimodal and symmetric. 61. Normal data is unimodal and symmetric. Thank you for all the people answering questions too. What percent of students in section A did better on exam 2? So now this is given someone is in section A, what percent did better on exam 2? So they have to be given in, so we're saying given someone is in section A, the percent they did better on exam 2. These might be better, what percent of students did better on exam 2? So now we go 66 divided by 87, and it's 75.86. Ooh. So this is 75.86. That's interesting. So exam section A is doing a bit better. If this is really what the exam will be like, I'm a happy lady. That is great to hear. What percent of the students? I think this is a good example. The exam can always be different questions, not like drastically different, but there's many ways we can ask questions. If you've been following along today, that's a very good sign. So thank you, everyone. Remember, look at the practice exam questions too. So no means they did not do better. Thank you. Oh, Cody and Nick. Thank you, Cody and Nick. Sorry, Cody, I missed your question right there. Always feel free to tag me. The N means that they did not do better on exam 2. So we're looking for the students who had Y for section A. That means students in section A did better on, and that's what I was calculating right here. I was saying if someone is in section A, they did better on exam 2. So that's 66 out of the 87 students did better on exam 2. Thank you all, thank you mods for catching that too. Sometimes a thing goes by, so always feel free to tag me in the chat with the name where you do @stat201 if you have a question, especially if you really want me to see it. Sometimes I miss something in the chat as I'm solving a problem. Thank you for all my taggers. Was B asking for exam 1 or 2? Oh my gosh. Wow. Wow. Look at that. So these are the students that, whoa, nice job. This right here, the students in section A who did better on exam 1, that is going to be right here. The students in section A who did better on exam 1, that would be these students. That was a good trick question. Not really trick, but caught me off guard. It's just going to be the complement of what we found a moment ago. My Red Bull energy is low. We need to talk to Red Bull. It's my ongoing theme. If I can get sponsored by Red Bull, I will. 21 divided by 87. We just need a Red Bull refrigerator like Ninja back here. I just open it up and just pull out a Red Bull. And we just have a graphic come in like, you know, oh, there we go. You know it had to happen today. You know it had to happen. So we just have it right here. So we can just have our Red Bull graphic come in. I do drink coffee. Coffee is excellent. I had coffee today. But Red Bull is just, I have become addicted to Red Bull. So what percent of students did better on exam 2? Now, if you notice, this is all the students. This is all the students. So all the students right here is as follows. So I think, Megan, thank you. You guys are double checking my work. So the percent of students out of all students who did better on exam 2 would be 96. We're going in red. We don't go in red. 96 divided by 136. And that looks to be the answer right there. That is, out of all students, I'm going to double check, but I think you're right. 96 divided by 136. 70.58. You are right, 70.59 when we round. So 70.59%. So what visual graphic or tool could you use? Oh, you know it. These two graphics hang out all the time. What two graphics hang out all the time? We know on the same data chart. So I'll explain, Serena, I'll go back and talk about this in a moment. They took the same test, meaning just different classes. Correct. We'll go back and talk about this just in a moment. But what graphic could you use to view this visually? Contingency tables go with what? It's a categorical display of data. It's a bivariate categorical display. You guys should know it. Mosaic plot, William, awesome answer. If you have two categorical variables, this test is very similar to the practice test length. Make sure you check out the practice test. Very, very similar to the practice test. Not this. These are just example questions. But the practice test is what it would be similar to. So these answers right here, it's like you would have, if we just erase this, this could be like Brian's section. So this would be something like here, like Brian's section and Missy's section. And then we ask students, did you do better on exam 2 than you did on exam 1? So these students right here would be the students in Brian's section who did better on exam 2 than they did on exam 1. These students right here would be the students in Missy's section who did better on exam 2 than they did on exam 1. And the contingency table is the graphic right here. Both are bivariate displays. So the contingency table shows you the numbers, and the mosaic plot shows you the visualization of it. So to get a visualization that looked something like this right here, this is what a mosaic plot looks like. It looks something like this. This one had a little bit of a relationship due to the gap. So the bigger the gap it has, like that one right there shows a very kind of weak relationship. And then over here, we'll draw one with a much stronger relationship by doing this. And we'll draw in, whoops, going out the bar there. I'd never draw inside the lines, never could have. And that one shows a much stronger relationship up top right there. How many questions does the exam have? Very similar to the, I don't want to go, I've seen it, I've obviously seen it, but I don't know the number off the top of my head. So yes, sorry, I kind of go through the descriptions quickly. And let's, all these great questions. Oh, yes. Oh, you have to do these. Report the mean. How do we get the mean of the data? Now, this is where I'm going to make another error, a little small error, not on purpose. Report Q1 and Q3. Oh, no. That's not going to be fun. This is where TI calculators come into nice use. 23 plus 2 plus 15 plus 4 plus 9 plus 18 plus 6 plus 22 plus 5 plus 27. And this data set right here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. 13.1, because you can see it there. So the mean is the sum of all the values, unless I've made a mistake. So right here, 13.1. Report the median. We need to put them in line now. So we need to go here and go and do a little work before getting there. 2, 4, 6, no 8, 9, 2, 4, 6, 9. Oh, forgot the 5. Truthfully, I could put it after the 6, but I shouldn't do that. We're about to the important numbers. You know what? We can if we do this correctly, we don't have to do any more numbers. 2, 4, 6, 5, 9, and 15. Okay, let's do the whole thing. 15, 22, 23, 18. Darn you, 18. 18, 22, 23, and 27. Yes. Are there 10 numbers? There are 10 numbers. So yes, calculator makes this so much easier. I have a video on the channel on using the TI calculator to do all these. Has anyone seen my TI calculator help video where it just shows you how to use the 1var statistics? Since everyone doesn't have a TI calculator, I'm just doing it here by hand. Thank you very much, people in the chat. Yes, we did it right. You should have 10 numbers written out. So you look, do I have 10 numbers? I have 10 numbers. Are they in order? They are in order. So now, since there's 10 numbers, there is no middle number. So we have to go here to number 5 and number 6. Just to make this clear, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The median is going to be between these two numbers because there is no middle number. If you have 5 numbers, the middle number would be the third number, but if you have 4 numbers, the middle number would be between the second and the third. So you can see right here that this is the middle point of the data set. So what you would do, I lost my 1 there on that 15. What you would do is you would add 9 and 15 to get 24. So 9 plus 15 is equal to 24 divided by 2, and you would get 12. So the median is 12, which is not a number on this data, but it is the median. It is right there. Now Q1 and Q3, we don't have you calculate by hand usually on the test. So Q1 and Q3, these ones are a little bit easier. If you notice how the data is kind of sectioned off right here, can anyone see where Q1 and Q3 would at? It is actually these middle points right here. Those are Q1 and Q3. Just look at it. They're kind of the middle of the bottom half and the middle of the top half. I'm not a big fan of those types of questions because not all data sets, usually the median's easy enough to see, but a lot of data sets are not as easily calculable on this. But it's kind of like you're taking the median of the bottom half and the median of the top half. Nice job, Megan, in the chat, giving those answers also. Thank you very much. So 5 is the answer in 22. And from here, we can get the IQR. So what would be the IQR? The IQR is just the distance between these two numbers. Let's go here in blue and draw this. So we're just going to do 22 minus 5, and that equals to 17 because it's Q3 minus Q1, and that equals to 17, or it equals to the IQR. We'll rewrite that right there. And people in the chat should be saying 17. Excellent, excellent work. We have now solved the practice work that Terry did. Thank you, Terry, very much. Are there any last questions? Are there any last questions? I'll stay here for another 3-4 minutes and go get some food. But what questions are there? Do you feel a little bit prepared for a little bit more prepared for the test now? Is there a little bit more prepared for the test feeling? How to prepare for the true and false questions? Oh, Gino, you ask the hardest of all questions. Yay, good job. I'm glad people are feeling more prepared. The true and false. Everyone hates true and false. That's all I can say is like true and false is like, well, algebra, not that much. Just add, subtract, multiply, divide. The biggest thing is the mathematical skills are not that high, as in if you have a good understanding of adding, subtracting, multiplying, dividing, you'll be pretty good, and using your calculator to find answers. But then interpreting, you notice we had to do a lot of visualizations, understanding how to use stuff. Can we look at one on the quiz 8? Yeah, which question is it? I'll do one quiz 8 question. So let me hop back here out of presentation mode, boop, and let me pull up the quiz 8. I'll do one question on quiz 8. I'm going to head out and go run around. So I cannot see the chat anymore. What does the question read on quiz 8? How does that question read? We are almost into quiz 8. And as long as the question's written out for me, or as long as I can see part of the question, we'll be good. So I'm getting the quiz pulled up as we're talking right here. And we're almost in. And let's go here to quiz 8. Let's do a practice problem on it. Preview. We're going to go to replace questions. And and let's see. So when I hop back over here, we'll take a look. Place questions. Okay. The quiz is now pulled up. And we should be hopping over to that. And I should be able to see everyone in just a moment here. Okay. So the question is on quiz 8. 100 years ago, the fastest cyclist. Okay, so let's go find the fastest cyclist question from 100 years ago. This one is a tricky one. Here we go. So here we are on the fastest cyclist question, and what we're going to do is we're going to take this data and we're going to bring it right into JUMP. Remember, this video will be posted for you to review to see how I'm doing this. I'm going to copy this data. Remember, it is posted, so if you're wondering, how do you get that data in JUMP? Watch the video and definitely pause it. So I'll start again, just so everyone knows. Watch, here we go. We're going to take right here, we're going to click there, click here, copy to clipboard, and then Control-C or Command-C on a Mac, copy the data, tab delimited, and then go over here to JUMP. Where's my JUMP at? My JUMP's not on my dashboard. Go over here to JUMP, and now we go to JUMP. We pin it to the bottom of the clipboard right here, pin to taskboard. Ooh, scatter plots. It knows what I'm about to do. I'm going to open a new data sheet here. I'm going to paste with column names. Please note that I pasted my data with column names, so you want to go to a new data sheet, File, New Data Sheet. Once you get your new data sheet up, you want to then edit, paste with column names. This is key because if you do not paste with column names, you will get something that looks like this. And JUMP is trying to show you right now with these red icons right here that these are categorical. If they are blue, then they are quantitative. And this is QQ straight enough, no outliers, because we're doing regression. So make sure to paste with column names. This is a tough one because the scatter plots are going to look very similar. So let's go ahead and make our scatter plot. We're going to analyze fit y by x. Let me slow that down. Go to Analyze. Fit y by x. And then we're going to go here and put year into the x, because that's what the graphic has. And then we're going to see if that can explain average speed, which is the y. We go here and we create our graphic. Now, I think we're going to go to the red arrow and go to fit line. Now, I want to point out something. Does everyone see this gap right here in the data? That's due to the world wars. There was not the events during this time period. So you see this gap in the 1940s that is around World War II, which this question will talk about. So there's this gap in the data right here, and I think that's going to be one of the key components which is going to help us find our right answers. So when you look at these graphics, well, this one, you see how it doesn't jump down there? Let's put my graphic beside it a little bit here. This one doesn't have the bigger bend. Do you see what I'm talking about right here? It doesn't have the bigger bend. Mine has like a swoosh swoosh and goes back up. Kind of looks like that one a little bit. And thankfully, it's going to be between these two over here. This one over here might be a little too bendy. Let's take a look at these two on the right. We're going to cross our fingers, make sure we get this right. This graphic has the missing data right there. This graphic does not have missing data. So this graphic does not look like mine, because remember, mine has the missing data right in here. Does everyone see that gap of missing data? So that is missing data. This one right here has missing data. If you notice this pattern, kind of goes like that. Let me look at mine. I think it's going to be the one on the far right. There's more of a gap, I'm pretty sure. And I'm going to give you a trick. You ready for the trick? The trick for this is that your graphic should have the missing data, and you really have to look at the ones very carefully, because one of them has kind of too big of a jump, and it does kind of look most like this one over here. It's a little hard to tell. You could trace over a number. You see how this hits at 25? I think that's the key. Yeah. The first point right here is at 25. That point right there is close to 25, and go to this graphic. The first point over here is at, that's below 25. See, 25 would be right there. That's tough. It's tough to tell the difference between those two. This one has the missing data, and if you look at the point right here, that hits at about 25. Very, very close. Very, very tough on that. Enlarge slightly. Yeah, that's a game changer. Yes! Keep asking those questions. Thank you for those who are like, oh, I didn't know you could make the graphic really big. I'll try to show you as matrix as I can. So describe the relationship between this. Well, the relationship is there's a general linear trend here. There's the gap with there's general nonlinear trend. Wait, here we go. The relationship is positive with a moderate amount of scatter. there is a general nonlinear trend with no races between this and no, do we have no 1918 races? 1915, 1918, is that World War I? Yeah, there's no races between 1915 and 1918. So maybe this one didn't even include the no races between 1915 and 1918. It looks like this one did not include that either. And then our graphic should have, look, a second gap. That's good. Our graphic has that second gap. And our graphic here should have a second smaller gap right here. So we are confirming once again we have the right picture. That is the right picture. So these both mention the gaps, so we're between answer B and answer C. So we know it's positive, that's for certain. And then I'm getting a little scared. The relationship is positive with moderate scatter. There is a general nonlinear trend. So all we're picking between here is there a general linear trend or a general nonlinear trend? And this is where sometimes I get a little worried. If you look at this graphic as a whole, what are they saying in the chat? I can't read it. I would say it's linear. I know, right? You know what we could do is we'd ask the question right here of Jump. Jump says, we'll see if Jump disagrees with my Pearson. This is something you wouldn't have to know. Ooh, let's go here. Where's his lack of fit? Do we no longer get lack of fit in here? Did they remove the lack of fit? Analysis of variance, and I guess they make you ask for lack of fit now. Or I don't know where to get lack of fit in Jump. Well, if I did it in R, I could get my lack of fit of the model. Maybe my eyes are just missing today. I am iffy on this is linear. Here's the thing. Do you see this trend at the start? It goes up, it goes down. Let's see what happens if I do this. Let's go to fit polynomial and fit this, and let's see what that looks like. There's kind of a spirally pattern to it. The answer is linear, but then the next one says it's not linear enough. Is that what it says? The next question? So there's kind of this nonlinear trend to it. And let me try one more thing. Let's go here to, do they not have flexible? Here we go. Fit a spline. And let's close this. Let's close this, and let's change this. It's kind of the cool stuff you can do in Jump. We're just having fun for the moment. Clicking the wrong button right there. So now we're fitting a bendy line through here. You can fit so many different things. So if you notice, is it saying it's linear? Because that's what it looks like to me. You know, because you got the next one wrong. So the answer is linear. And let's see. Okay, so thank you, Adriana. It's saying it's linear because those are the iffy ones. We've got ways with dealing with these problems for advanced stuff. But so it's going to say it looks linear. And now we need the regression equation. So the regression equation is, it's gone now. We'll get a new cool colored line here. So let's go to fit the line in. And the regression equation is right here. So we get the regression equation. Let's go grab the regression equation right here. So, oh no, Serena, these questions can be a little tricky. So let's go in the intercept. If everyone sees where I'm grabbing this equation from, let's make it full screen, double view. The equation, oh no. There's the equation right there. Now it's going to get mad at me. This one's also tricky. A few people in Office Hour missed this. Watch out. This one wants it to 3. This one wants it to 2. So that, if you notice, be careful. It says here, round this one to 2 decimal places, and then it says round the coefficient of year to 3 decimal places. Are the conditions for regression met? Oh, that is so weird. So then it asks you about the conditions, and the answer is going to be no. So people are telling me in the chat that it's going to say, my section should be in A and B auditorium tomorrow. On the test, we have to calculate the answers for. You will not have to calculate the slope or the intercept in test 1. You will have to, this one is B. No, the relationship is not straight enough in the early part of the 20th century to fit a regression line. The variables are quantitative. Yeah, the variables are quantitative. That's QQ. And there are no real outliers. That's good. But it's saying it violates straight enough. Let's check answer. 100%. I might have to, that's so interesting. I agree with you guys that there is a general linear trend. They should change this right here to say it becomes linear after. If you look at this, there's a linear trend starting about here, and then this is flat. So I do agree, and that might have tricked me too. This would not be an amazing test question because it's a little hard to be like, is that linear? And the answer is kind of. And so the kind of ones are the harder ones. We do have ways of analyzing this data. And let's see right here. I'm going to do something really fun. We're going to end class with some real fun because I'm going to go and really do this problem for our last little bit. We're going to go to export this file. Where's the export on here? Save as in this version of Jump. So we're going to save this file, and we are going to save it as a CSV file. And we are currently in the downloads. Perfect. Let's call this my peer. Is it opening? There it goes. My Pearson. Okay, and then let's just call it data2. Okay, data2.csv, we got it. Okay, it's opening in Excel. We're just gonna have a tiny bit of fun here because we're gonna open RStudio. So if people know my class, they know my love of RStudio because this is the way I would actually analyze it. So we're gonna find out the real deal with this regression. We're gonna figure out what's really going on right here. We're just gonna get a cool glimpse of what we can do with statistics because I was like top at these things. Let's just call this data. And let's do read.csv. And what did I call it? Data1. We'll find out the hard way if I called it data1. Data1.csv. It's not called data1.csv. What did I call it? We called it, of course I forget what I call it right after I call it that. Am I in downloads is a good question too. Data2, why did I call it data2? I guess I thought I had data1. So let's see right here, data2.csv. If I'm in my downloads folder, which I should be, cannot open. Let's go to files. And let's go to sessions, set working directory. We'll be done in just a moment here. And we were in documents. We want to be in downloads. And now we're here. OK, cool. And so let's go over here. And let's take a look at this. And what's the name of our variables? And oh my gosh, it's got to be crazy names. Names, data. Let's store into these names. Let's call them different names. Let's call it year, and let's call it average speed. So this right here, you will not need to do any of this on your test. We're just having fun to end because data is amazing, and it's easier, I think, in my mind, with programs like this. So we are going to make a linear regression right here. So remember a moment ago in Jump, your output can be seen right here. This is the same output we were getting in Jump, where we're predicting year, average speed. There's the coefficients. It's just doing it in scientific notation right there. But the really great thing about this, I'll answer questions in 2 seconds here. Oh, we got to do one more thing. So let me see here. Let me look at some questions while this runs, because I really want to know if this is linear or not. So let me answer all the questions. The questions you messed up, I'm sorry. I think the general thing to do is 2 decimal points. That is correct. But when doing all calculations, keep them on the rounding. So if we have to put the numbers in the regression equation but not come up with those numbers. Laura, you are correct. Our standard error questions on the exam. Standard error questions are not on the exam. Standard error questions are not on the exam. So here we are. What we have right here is our linear model. Does everyone remember that graphic we just saw over there? There is our linear model. And we can also check to see if we would need to choose a model that is a polynomial model. So does everyone see the bending through the model? This is why I like all these things we can do right over here with code. We can see how well our model is doing. And last but not least, we can go over here to check regression, which checks to see if we have a good regression. And the answer is we can't actually run the test. No! Oh, because it's a time series. If anyone's watching this for another thing, that's a time series and it has no duplicates or replicates. Darn it! But there's the residual plot. So if you look at the residual plot right there, if you remember the residual plot has a center of 0, you see the bend through it, all that good stuff right there. But my favorite thing to do is this, is to go to the choose order graphic and just go crazy and do something like 15. And now you get all those colored lines right there. It looks so cool. It looks like Laffy Taffy or something. But that's a 15th order polynomial model. But this is one of the coolest codes right here. It lets you, remember how I was fitting those bendy lines through the model? This is doing the same thing. And the red one, the 10th order, really picks up on the bends through it. So there is some sort of bendy pattern through it. And you see you've got your things like R-squareds, and the R-squareds keep going up. So by virtue of the R-squareds going up, this is, if anyone's watching this for another class, this is not on your test. By virtue of the R-squared adjusted going up, by including higher order polynomial models in the Akaike information criteria, which you'll see over there on the far side, That's these values over here. By virtue of them going, R-squared adjusted going up, and Akaike's information criteria going down, these higher polynomial models are better, and we could get an idea of what model to do by doing this. This is just kind of the cool things we can do with code, and funny enough, I kind of stopped at the right point because it looks like a 12th order polynomial model is the way to go, and just, it looks so cool to me. I just like seeing the graphics. I'm huge into graphics. How many people do we still have here? Did I lose everybody? They saw coding, they're like, no, run away. But this is all the same things that we are doing. But think about this. In code, if you want to find your residuals, for your model in code, all you have to do, let's make this go down. There we go. To find your residuals for your code, all you have to do is residuals of your model. So we could do the residuals of our model, and there's all the residuals. We can get predictions for our model, and there's all the predictions. So that runs all the equations. So a lot of times, especially in a lot of different statistical classes, we're not just solving the equations by hand. You don't do a lot of solving of statistics by hand, especially when you're just doing math and statistics, or statistics, I should say. Statistics is more done via code, and to me, it's like a video game, and when I get something to work in code, I'm like, yeah! I got that cool graphic. I've got that choose order graphic that looks like Laffy Taffy. I like it. It looks awesome right there. So to me, this is fun, and I hope you guys and gals had some fun today. Is anyone still here? Did I lose everybody? Let's see how we're doing. Copy video URL. I will say goodbye, and we just had a little bit of fun here at the end. 28. Thank you so much for everyone being here and watching. Remember to email me if you have questions. I'm going to go back and answer emails now, but if you have questions, go ahead and email me. Any last quick questions? What formulas will it go through? The formulas are on the formula sheet. So thank you for everyone for coming, watching the video. I just want to throw on this at the end, have a little code for fun. I know not all. What formulas will be on it though? I think the residual formula for the E equals Y minus Y hat, and also the, oh, you're welcome, Kate, and the Y equals B0 plus B1x1, or B1x, sorry, in our class. So we'll write those right here. Well, we can go to slide here. That would be, so residual equals Y minus Y hat, and the predicted Y is equal to B0 plus B1x. I think that's what's on there. Great job. We'll end off here. Thank you all very much. Have a great evening.